Hi guys, today we are going to see for the fourth case, okay, of a non-differential, non-exact differential equation, okay. So when an equation it's not exact, okay, and it cannot be solved by the first, second, third case, so we can try for the fourth case. It's not a problem at all. Okay, yes, it's not a problem at all. So in this fourth case, it is the same of the third case. Okay, it's the same of the third case, but what we are going to change here, it is only one thing. So in the third case, as you can see, in the third case, we just work IF, integrating factor, okay, is equal to Euler raised to f of x dx, okay, where f of x was a function of del m del y minus del n del x upon n. So for this fourth case, it will be f of x y, or f of y dy, and f of y, that is a function of y only, will be equal to the opposite of this one. And here, instead of n, we will put m. This is what we are going to see here, okay. For fourth case, okay, the integration or the integrating factor will be equal to Euler raised to integration of f of y dy, where this f of y is equal to del n upon del x, okay, del n upon del x, not del m upon del y. Just be careful, here it is the opposite, okay, del n upon del x minus del m upon del y divided by m, okay, where f of y is a function of y only, okay. Yeah, after finding this IEF, the integrating factor, so you can solve by this one. So this is the fourth method to solve a non-differential equation. It's for fourth case, okay, case number 4, okay. And again, what we are going to see is just to solve for see the difference between this case, it is only in how to find the integrating factor, because after finding what is the condition that is fulfilled here, that I can apply and solve and find the integrating factor, the rest is the same. All the steps will be the same steps, okay. It's okay. Now see, after finding the integrating factor is Euler raised to integration of f of y dy, where this f of y equal to del n upon del x minus del m upon del y and upon n. So after finding this, you're going to multiply this integrating factor and find the solution of this differential equation by using the exact method solution of this differential equation. Now let us solve for this one in this case, okay. Let us solve for this one of these exercises. We can start by this and this, okay. It's okay. Let us start for solving this one. Suppose we have this expression here, okay. It is in form of m. If you can see, it is in form of mxy dx plus n of xy dy. It is in this form directly, okay. But this one is not in this form. So when they give you in this form, you directly just can find what is m and x and just check whether this function is exact or not. But when they give you like this, you have to transform in this function, you transform this equation in this form, okay. So we are going to solve for this one. For this one, you can check home and it's okay. After you seeing how to solve this, you can go for this one. It's fine. It's okay. Now see, this equation, it's not in form of mxy dx plus nxy dy equal to 0. So we have to reduce this in this form. The first step is this. So what you're going to have here, you're going to just put together all the x's, okay. All the x's must be together. So x Euler raised to x plus Euler raised to x dx, this and this, and this one and this one. This will be plus x Euler raised to x, okay, plus, sorry, it is minus, yeah, it will be minus, but yeah, it's okay, minus here, plus y Euler raised to y dy equal to 0, because this one and this is minus, so this will be minus also. Now that you found this one, it's okay. Now you can say this is m xy dx. You can compare now, and this is n xy dy equal to 0. Okay, now you can say that m is equal to x Euler raised to x plus Euler raised to x, and n is equal to y Euler raised to y minus x Euler raised to x. Is that okay? Find what is del m with respect to y, and find what is del n with respect to x. So here, if you find with respect to y, it will be 0, no terms in y. And here it will be minus Euler raised to x and minus x Euler raised to x. Okay, just like this. Because this one will be 0, so this will be a product, then just apply the product of differentiation. So now that we find this one, okay, so this is okay. Now that we found this one, so what's the next step to be followed? Okay, yeah, we said that here del n del y is different of del n del x, so it is not exact. So to make it exact, that's the point. What will be our IF? What should be the number that we have to multiply by the whole expression here, so that this expression can be reduced to a exact differential equation? That's the point. Okay, how to find this IF? And see, here in the fourth case, we have to check first if this equation is not satisfying any of these 3 points that we have found, any of these 3 cases that we have solved. Okay, okay, let us see. So x Euler raised to x and Euler raised to x, is this a homogeneous function? No, surely it cannot be an homogeneous function, because they do not have the same degree, and it's impossible to reduce them to the same degree. Secondly, is that a function of x, y, x times y? No, because here I do not have a function of x times y, x, y, I do not have this one. Third, is this equation can be reduced to a form of, we can just take del m, okay, del m del y minus del n del, y, del x, and we can find a function of x only. Just do this and this minus this will be this expression, positive, positive. But the point is that we have to reduce to divide by n. If we divide this one to this one, this will be impossible to have an expression of x only. So we can apply now the fourth case. Okay, what is the fourth case? The fourth case says that when we have this expression like this, okay, first we have to find what is f of y. F of y will be del n upon del x minus del m upon del y, all upon m. This must be a function of y only. If this is true, if I can find this function of y only, then it will be easy and it will be fine for me. Let us try then. This will be del n del x, it is minus Euler raised to x minus x times Euler raised to x, then minus 0 del m del y, all upon m. What is m? That's the point. M is equal to x Euler raised to x plus Euler raised to x. Okay, so if you divide this one, let us see, this minus, you can put this one, you can factorize minus 1, and this will be Euler raised to x plus x Euler raised to x. Oh man, you can see that it is true. Okay, this is true, plus Euler raised to x. So this and this can be cancelled out. This will be equal to minus 1. It means that here f of y is minus 1. If f of y is minus 1, what does it mean? That's the point. It means that f of y is minus 1, so IF will be Euler raised to f of y dy. Oh, sorry, dy. Okay, dy. So it will be equal to Euler raised to integration of minus 1 dy, and this will be Euler raised to minus y, and this is 1 upon Euler raised to y. Okay, this is our integration factor or integrating factor. Now that we know what is our integrating factor, we have to multiply the integrating factor for both sides, okay, of these equations. So integrating factor multiplied by them, it will be Euler raised to y, okay, x Euler raised to x plus Euler raised to x dx plus this will be y Euler raised to x minus x Euler raised to x dy. This will be multiplied also by Euler raised to x, and here it is 0. Okay, just multiply as you can see. After this multiplication, what you're going to see, okay, just do the simplification. This will be x Euler, okay, x Euler raised to x. This will be x Euler raised to x, okay, minus y plus Euler raised to x minus y, okay, dx plus here the same, just do the same, it will be y minus x Euler raised to x minus y, and dy equal to 0. If you find del m1, del y will be equal to del n1 del x, okay, will be equal. So then what's the next step? Just integrate this and integrate this, okay. The first integration will be for y constant, okay, for y constant. Then you'll get y x, this one minus y, okay, then plus Euler x and minus a1, and this is dx plus integration. Just you have to excluding terms in x, and here what you are going to have, this term is in x, so this term all will be 0. So you have only y dy equal to c. Here it is c. Okay, what's the next term now? This one, okay. What you have to do, just find what is the differentiation, what is how can I say, the integration for this one is see, as y is constant. If you see here, okay, this is the case I was looking for, guys. See this integration, okay, you can solve, it's fine, you can solve by applying this what's the name, substitution, not substitution, by applying integration by parts. Here easily you can solve, and here you can solve. But if you're not acquainted with integration by part, what you have to do, you can do also come here, you can also come here and make it the opposite sides, okay, that's okay. Let us solve for this one. So x Euler raised to x minus 1, this is y is constant, so this y is constant can be down and so on and on. Here it will be 1 upon Euler y and x Euler raised to x, okay, dx, okay, plus then you can solve also for this one, 1 upon Euler y and Euler raised to x dx plus integration of y dy equal to c. This integration, so we know that this this integration can be solved like this. Suppose here it's a polynomial and here it is the integration, okay, the integration of Euler with respect to x, okay. So first we find the first one, this is px is equal to x, okay. So px derived, it will be 1, and here integration of this one will be Euler raised to x, okay, this and this. Then integration again of this guy, okay, integration again, because here we have two expression, two polynomials, so we have to integrate this twice, and this will be Euler raised to x. So just integrate this one. If you do this, you will see that you will end with an expression like this. Then just link this and this. See, in this method you have just to do it is the same. If you feel like you can do it by parts, you just do it by parts, fine. But see, what we are going to do, what we are doing here, this Euler raised to x, it is an integration constant. Okay, it's a constant integration because it will be the same, and the same. Even if it were something like cos and sinus, it will be something repeated again and again and again. So you can do this function with this. Okay, so make Euler integration and make px the polynomial that we have here. Then find here the derivative. First px, then the first derivative till you find it 0. Then just go and find the integration of this, So here we have two polynomials, integrate twice. Okay, then link it. The first will be positive and the second will be negative, just like this. Positive, negative, positive, negative. So it means that this integration will be equal to 1 upon Euler raised to y. Okay, equal to, this will be this time this, x Euler raised to x, minus this time this, Euler raised to x. Okay, plus 1 upon Euler raised to y, and this integration is the same, okay, plus, and this integration here, it will be what? Y squared upon 2 equal to c. Now just sum all of them. You can just sum. This will be 1 upon Euler raised to y, and this guy can come here, as you can see. Okay, this guy can come here. This is okay, and this is fine. If you come here, this one here, this will be x Euler raised to x and minus Euler raised to x plus Euler raised to x plus y squared upon 2 equal to c. This one and this one will be cancelled out, so you will end in this one, Euler raised to x, and here x Euler raised to x plus y squared upon 2 equal to c. Here you can simplify. This will be 1 x Euler raised to x minus y plus y squared upon 2 equal to c. Okay, so if you are in doubt about this method, you can just do this by part, and it's okay. So okay, this is one way. This is the way to solve this one, this exercise. Now try to solve for this fourth case. Okay, for this fourth case, let me see the other exercise. Try to solve for this one. Applying the same method, and check whether it's fine or not. Okay, and it usually will be fine. Okay, thank you. See you when I see you, and in the next lecture or in the next video, we are going to study the fifth case, this one that you can see here. Okay, I hope you may enjoy this one and it can be helpful for you. Thank you very much. See you when I see you.